So I'm going to try the mic and we'll see how it goes. So this study behind me was published in August 2015. In it, psychologists conducted 100 exact replications of previously published studies. Only 36 of them replicated successfully. That is, got the same statistically significant results as the first group. Even worse, only 47 of them have results that fell within the 95% confidence intervals of the original studies. Now, if the original studies were done correctly, we could expect 95 of the replications to fall within the confidence interval, because that's what a confidence interval is, but only 47 did. Other studies have shown failures of replication in other scientific fields. The largest problems have come in psychology and medicine, which is especially worrying. So, this seems like a pretty big problem for science. A lot of scientists have ideas on how to fix it, like requiring larger sample sizes, pre-registration of trials, having stricter criteria for p-values. All of these ideas and more are worth exploring. The theme of this TEDx event is questioning the norm. I will argue that the problem goes deeper than just specific research methods. Instead, the problem is statistically significant and reject the null hypothesis, which lends support to our original hypothesis, H1, being true. As an alternative, I want to advocate using a different kind of statistics in science, Bayesian statistics. Bayesian statistics makes heavy use of the Bayes theorem. Here it is. So this is kind of complicated, so we'll go through each term individually. The first term is P of E given H. This is the probability, assuming that our hypothesis is true, that we would get the data that we got. Next is P of H. This is the prior probability in our hypothesis being true before we collect our evidence. We're doing science. This is how confident we are in our hypothesis before we go do our study. Next is P of E. This is the probability that we would get the evidence that we got. So when we put all these terms together, we get the term on the left. P of H given E. This is the posterior probability that our hypothesis is true, given the evidence that we ended up getting. So when we're doing science, this is how confident we should be in our hypothesis after we've done our study. So it turns out that we can use any hypothesis here, even the null hypothesis. So that's what frequentist statistics does, except they only use one term on the left, P of E given H, not P of H given E. Now, these are not the same thing. The probability that I'm wearing a shirt, given that I'm wearing a red shirt, is 100%. The probability that I'm wearing a red shirt, given that I'm wearing a shirt, is not 100%. In fact, seems to be quite low. So, this is the main problem in frequentist statistics. It's measuring the wrong thing. Instead of measuring the probability of our hypothesis given our evidence, we're measuring the probability of getting our evidence given some hypothesis. This is just totally backwards. So let's walk through an example to help make this more concrete. Let's imagine we have 4 coins. 3 of them are fair, and 1 of them is weighted, so it will land heads 80% of the time. So let's pick a coin at random, and then try to determine using evidence of coin flips whether the coin we picked, whether the coin we picked is the weighted coin. So we'll flip the coin, and it's heads. So now how likely do we think that it is that the coin we picked is the weighted coin? Well, let's try our frequentist method first. Our hypothesis would be that the coin is weighted, which means that the null hypothesis would be that the coin is fair. So what's the probability, given our null hypothesis, given that the coin is fair, that we would get the data we got, that we would get a heads? Well, a fair coin lands heads 50% of the time. So P equals 0.5. Now, if we use the standard scientific significance level of P is less than 0.05, then this data is not statistically significant, which means we can't learn anything from it with a frequentist method. With a Bayesian method, however, we can make a meaningful conclusion. Let's use Bayes' theorem and try to update our beliefs. So here's Bayes' theorem again. We'll do each term one at a time. So first we have P of E given H. This is the probability, given our hypothesis, which is that the coin is weighted, that we would get the heads. So if we have a weighted coin, it will land heads 80% of the time. So this is just 80% of coin. Next is P of H. This is the prior probability that we have the weighted coin. Since there's 4 coins and one of them is weighted, this is just 1 in 4, or 1 in 4. Last is P of E, excuse me. This is the probability of getting heads before we do any coin flips. So there's a quarter chance we'll take the weighted coin. That will end as 80% of the time. And then there's a 3/4 chance that we'll get one of the fair coins. And each of those will end as 50% of the time. So we can take all these numbers, put them back in a Bayes theorem, and do the math. Turns out there's a 35% chance that the coin we just flipped is the weighted coin. So let's compare. With the frequentist method, we weren't able to make any conclusions from our data. We weren't able to learn anything. With the Bayesian method, however, we were able to make an inference. We changed our probability that the coin that we had was weighted from 25% to 35%. This is the main advantage of Bayesian statistics. In frequentist statistics, all inferences are black and white. Either a result is significant or it isn't. All frequentists can do after they flip the coin once is say that they need to collect more data. On the other hand, a Bayesian can make inferences in shades of gray. A Bayesian can also go collect more data to be more sure. But right now, they haven't answered the question, how likely is it that the coin we just flipped is the weighted coin? So it turns out that figuring out what the prior probability of our hypothesis should be is a lot harder than it was usually, than it was in our last example. So when we're doing science, the prior probability is usually subjective, depends on the judgment of a researcher rather than a strictly objective method. This means that different scientists are going to have different prior probabilities about the same hypothesis. So with this in mind, it'd be a bad system if what science were to publish were probabilities and hypotheses being true, because those would depend on subjective probabilities of individual researchers. So depending on who did the study, we'd get a different number. Experiments themselves are objective and produce objective results that shouldn't depend on the researcher. So let's go back to our coin example, except this time we don't know that there's only 4 coins. We don't know the prior probability. We're just picking a coin totally at random. All we know is that it's either weighted to land heads 80% of the time or that it's fair. So what can we do here? We can calculate what's called the Bayes factor. The Bayes factor depends only on the experimental result. If we have 2 hypotheses, say H1 and H0, then the Bayes factor is P of E given H1 over P of E given H0. So with our coin, if H1 is the hypothesis that the coin is weighted and H0 is the hypothesis that the coin is fair, then the probability that we'll get heads if the coin is weighted is 8% at 0.8. The probability that we'll get heads if the coin is fair is 50% at 0.5. So the Bayes factor is just 1.6. So what can we do with this? Well, we can multiply our Bayes factor by our prior belief in order to calculate what our posterior belief should be, what we should believe after we've seen the evidence. So Bayes factor, that's what we actually want to use in science, because that's actually objective. So instead of trying to make inferences or get results that are statistically significant, we want to get results that change our beliefs in the direction of truth. This is what the Bayes factor lets us do. So you might be thinking, is it really a problem that we can't make any conclusions by looking at a coin just once? Maybe you're okay with science needing to go collect a bunch of data before it makes any conclusions at all. There are times, however, where we only get one data point. Take the following problem. 10 out of every 1,000 women have breast cancer. Of these 10 women with breast cancer, 9 will test positive. Of the remaining 990 women, 89 will also test positive. A woman tests positive and wants to know whether she has breast cancer for sure, or at least what the chances are. So this problem was presented to over 4,000 doctors. Well, this is actually not too hard to solve using Bayes' theorem as we were doing. So we'll say the hypothesis is it's a woman with breast cancer, and the evidence is that she tested positive. So we can just use Bayes' theorem as we've been doing. I won't go through all the steps this time. Turns out there's about a 9% chance the woman has cancer. Here's the problem. Only a quarter of doctors answer this question correctly. This is a multiple choice question, 5 possible answers. Another full quarter of doctors said that the woman had a 90% chance of having cancer. That's a huge difference of something to tell your patient. That's not good. So the reason that so many people made this mistake is because they're confusing the probability of the woman testing positive, given that she had cancer, which is 90%, with the probability of the woman having cancer, given that she tested positive. This is the same problem we saw earlier. Frequentist statistics is measuring the wrong thing. It makes total sense these doctors would make this mistake, because they've been doing frequentist statistics all their lives. So the 90% value is the probability they're usually trying to calculate. So the lack of exposure to Bayesian reasoning makes this problem much more likely to be done correctly. So I use this example both to show that Bayesian reasoning can be valuable, but also that we can't always go collect more data. Each woman only got tested once. So we've seen several advantages to using Bayesian statistics, rather than the standard frequentist statistics used by most science. If science used Bayesian statistics, people will be better at Bayesian reasoning, and they do better at the kind of problem that we just saw. Science will be able to make conclusions based on all the information at its disposal, not just statistical significance. We'll be able to make conclusions that weren't just black and white, but could come in shades of gray. And most importantly, we'll be able to have scientifically informed beliefs about hypotheses, beliefs about the way the world actually is. Thank you.